block might be working. So we said how to increase the data rate. Okay, so how can we increase the bit rate? So we looked at different issues. Designing aim was to look at the design issues. Actually, it was the design we were looking at. And then some of the timing properties that may cause my system not to operate because of violations. So that is what we were looking at. Aim was to look at the digital systems engineering. Right? How to make a system work. We were assuming that the basic fundamentals are already known to you. We were developing on that. So now, one thing is now moving ahead from designing. That is, if design is now, things are known to me, how to develop a synchronizer, I/O drivers, clock distribution network, PLL. I have designed everything and my pipeline system is working. Okay, now comes, okay, this is one specific design, complete design, where I am saying that, okay, this design will work. Now I am going inside. So suppose I give you a top level view, starting from the processor. A digital processor will have different blocks like memory, input, output, circuits, memory, control, data path, everything will have. Now within the data path, if I go inside, okay, so within this data path, we will have arithmetic logical unit which does all the operations. I'm not looking at instruction decoder now, instruction fetcher, instruction decoder, instruction execute, because they will all be a part of a complete process. I am saying, looking at the architecture of one particular block, and my block here is going to be a focus point will be on arithmetic blocks. One circuit or the block which is doing arithmetic operation. Similarly, you can also have a focus on the block which is doing logical operations. So now my aim is to give you a flavor of choosing right architecture for a given block. And then designing issues we have already. How to develop a pipeline system once the architecture is clear in my mind, that I can do, and now I know the issues very well. So I am saying how does choosing right architecture is very, very required. And what is the impact of choosing the architecture on the performance? And in that you will see two major blocks which are very, very frequently used. That is an adder and a multiplier. Adder is a modified, or subtractor is a modified form of adder now. And similarly, divider is also kind of, if you have developed adder and multiplier, divider can also be, because divider is kind of a subtractor. Repetitive subtractor. Okay, so if I know the fundamentals of adders and the multiplier architecture and its impact on the performance, architectural impact on the performance, I can very well extend the same principles to subtractor and divider. You can also go in for that kind of a system which calculates the trigonometric functions. What do we call that block as? Chordal. They are also a kind of a multipliers and adders only, which are actually implementing a chordal. So implementing these basic units, understanding them completely, and then translating them onto the more complex designs, building upon that. So I will be showing you very basic functions, addition and multiplication, and you will see how we will tweak the architecture, how we will use number system to help us in achieving a reduced delay, a high performance adder and a high performance multiplier. Simply playing with the architecture, nowhere now I will be talking about the design. Transistor level design I will not be talking. The impact of architecture, choosing the right architecture, innovating the architecture. Okay, so mostly working at the top level, not at the transistor or the layer. Clear? So as we say, my focus is on arithmetic units. Yes, there are other blocks also like memory, control, interconnect. Whatever I would be telling here, you can just extend the scope. Can also include, you can also have an architectural impact on memory, control, interconnection. Same way it has to be translated. But in this course, we will be only looking at mostly adders, multipliers and shifters. Adders, multipliers and shifters. Okay. Now let us see how a adder or a simple ALU is designed. has arithmetic logical unit, and normally it is designed in a bit sliced way. This is how it is designed in a bit sliced way. Like all your inputs would be, so this is like you have, normally we have all the bits. So bit 0, bit 1, bit 2, bit 3. Okay, I can show you here. So we have a data in coming from here, getting registered in the, stored in the register. Then addition happening, then shifting happening, and then multiplexing happening. And then you are getting your data out, and all your control signals coming vertically from the vertical positions. All your data in coming from the left side, all the data out going from the. Now you can have a change here. You can have a control coming from below. You can have a data in here. You can have a data out here. But more or less, it is going to be a kind of an architecture where you fix one side for data in, one side for data out, one upper or lower maybe for control, so as to have easy layout of the wires, easy layout of the interconnections. And then you can easily look at, you can easily find out, configure that which is coming from which side. Ease of design. So normally a kind of design that we get in somewhat of this nature. Okay, this is known as a bit sliced way. Bit sliced way. Okay, bit sliced architecture. So within this bit sliced architecture, we have data in, as I said, data out, and then all your blocks within, you can say, arranged in a horizontal fashion. Here 3 blocks are shown: adder, shifter, and multiplier. You can include in a similar way other blocks, riser, chaotic algorithm block, architectural. So all these things you can also include. They will be arranged in a similar horizontal fashion. Okay, and then naturally all the layouts, interconnections, they would be carried out from left to right, or for all the control signals moving from top to bottom. Okay. Now, if I look at the simplest block, very simple block, we all know. I think many things you would already be knowing, but we would be carrying out our journey right from the very basic to the very complex, where I would be using redundant number system to achieve a very sophisticated adder, which is actually does not have any carry. Which my aim is to make the carry domain zero. So we will be making, because we will start making changes in our normal, simple, basic RC architecture, and we will see till how long we can go by tweaking. And then if it is no longer further yields any result, I will start modifying my number system and then start designing different types of adders. Aim is, everywhere the aim is to reduce the delay, increase the performance. Okay, so many issues will be already been known to you because you have already done those blocks. But we will be simply going through it just for the sake of control. This truth table is known to all of you. Okay, so we have a full adder, basic unit of an addition unit, 1 bit adding. So we have the operands A and B, 1 bit operands. We have the sum output, we have the carry output, we have the carry in. Okay, truth table is given in this form. You may have a carry in 0 or 1. Depending on, you can have AB combinations, and then when you find out, you can find out this is the final output for sum and this is the final output for carry. Anybody can say this requires a XOR implementation, this requires a XNOR implementation, this requires which implementation? NAND, and this one? So combination of these two will yield C0. Now you can also represent it in terms of generate and propagate. We can also represent the whole truth table in terms of, not in terms of sum and carry out, in terms of generate and propagate function. So generate means there is no carry in, we all know, but a carry out is present. That means a carry is generated, the operands are such. So we can say now here you can say 0, 0 is 0, there is no carry generation. Okay, even if there had been a carry, even if you have a carry, even then carry out is 0. It is a kill function. It is a carry kill or carry delete. That even if carry in is present, carry out will not be there. That means operand values are such that it will absorb the carry. So it is a carry kill or it is a carry delete. These are two comes under delete function. These two come under the propagate function. Carry out, whatever is the value of carry out comes to Carry in comes to carry out, and then there is a generate, that is there is no carry in but there is a carry. And then you can represent your sum and C out in terms of GP functions, GP. You can write those equations, generate, propagate, and sometimes you can also represent in terms of kill if you want. Okay, generally we can write in terms of generate and propagate. So these are the equations that we start with, and we use this equation to get our first architecture, that is a ripple carry adder, where you are using simple these equations, which is the previous one, or you can also use the equations in terms of generate and propagate functions. You can implement either way. Either first get a generate function, propagate function, or you directly use a transfer level diagram to get the sum and carry output by using A, B and C inputs. Whichever way you implement, it's up to you. A full adder you need to design, because by putting many full adders together, you can design a parallel RCA. So 4-bit RCA, where 4 bits you can give simultaneously and 4 outputs are generated. Or you can have 8-bit RCA, 16-bit RCA, 20-bit RCA, whatever you have. The drawback, we all know what's the drawback of this structure? That it is not the problem of sum which is a problem, because a final carry cannot be computed unless all previous carries are generated. That means final sum you cannot compute unless you have the n-1th carry available. And this is the point which takes maximum delay. This is the path which takes maximum delay. And which combination of operands will give you the maximum delay? Which combination of A and B will give you maximum delay? First bit generate and rest all propagate. First bit generate and rest all propagate. So this is our worst case delay combination, and our delay is governed by this condition. Okay. So you can express the total adder delay now. If I represent my total adder delay and there are n bits, so first of all carry all n-1 carries, compute all n-1 carries, and final compute last sum bit. So n-1 time per carry computation plus nth positions t sum. Nth position t sum. And we can see if n goes on increasing, the delay goes on increasing. So here the time delay is a function of n. Simple n. Go on increasing n. So if I ask you now to make or find out a PG diagram, propagate, generate diagram, that means assuming that you are implementing every full adder by using P and G functions. Okay, then you will find a propagate and generate function at the 0th bit, at the first bit, at the second bit, and then you are finding your sum and carry by using these equations. By using these equations, you will be finding out. So all at every full adder position, I would be finding out a P and G functions. All P and G functions can be computed simultaneously. Do you need a carry in there? Do you need a carry in to compute, generate and propagate functions? What is a generate function? How do you find generate function? If both are 1, generate is 1. So it is simply AND operation. It is simply AND operation. And what is a propagate function? It's a 1-0 combination. If A is 1, B is 0, or A is 0, B is 1, both ways propagate will be 1. So it is a simple XOR operation. And kill will be when both are 0. Okay, so we know the equations. Equations are only, P and G equations are only dependent on A and B values. Carry has no role to play. So I can compute, because it is a parallel adder, I would be feeding in all my bits, 16 bits, A0, B0, A1, B1, A2, B2 simultaneously. They are available to me. And they are going to each full adder, and then immediately you can compute in the next step all the P functions and the G functions. You don't require a C. So this all step can be simultaneous. I can say this requires only 1 unit delay. 1 step delay for computing all, so it is a 16-bit RCA. So 1 unit delay for computing all 16 position G and P functions. They are all independent. And then now comes the computation for sum and carry. Okay, now this will take time. This will take time. So if I draw a PG diagram, carry ripple PG diagram, 16-bit position, 0th bit you start computing G0 and P0. So at this position you have a P0 and G0 available to you immediately. P0 and G0. Now one thing you can also, one way is that everybody computes G and P function compute, and then it is a C which is diagonally going down and down and down. One way I can do that. This is one way of represent. I have a G0 P0 available here. I have a G1 P1 available here. A G2 P2 available here. And then the next is I come C0, Cin is there, which I can use to generate a C0. From there C1, then C2, then C3. So either you draw it in that way, or what I do is that I have a G0 P0. Okay, I use it to compute the block of 0 and 1 together. Generate for 2 bits together. Generate for 2 bits together, get me G0. Generate for 3 bits together, 0, 1 and 2. Gives you G0, 2. Generate for 4 bits together from 0 to 3. G0, 3, G0, 4, G0, ultimately G0, 15. How does it help me? Or what does it indicate? Why am I generating block generate function? Because carry would be simple. How do you compute G01? How do you compute C1? What is the C0 equation? C0 is G0 plus P0 into dotted with Ci. What is your C1 equation? Now you replace G1 P1. What's the G1? If I want Z01 is available to me because it is G1 plus P1 into C0. Now C0 is not known to me. I need to wait till C0 is created. What is known to me is Ci. Right from the very beginning, Ci is known to me. So let me represent all my equations in terms of Ci. Something which is already known to me, I don't have to wait. I don't have to wait. Now look here. G1, P1, independently you can compute. You need not wait for any carry output. G0, P0, all these values immediately you can get in one step. Now G01 will be simply a combination of G0 and G1, which is independent of carry. I can independently calculate the G01. I can independently calculate G02. I can independently calculate. Once these block generate functions are available to me and block propagates are available to me, just mix it with Ci and get your C1 or C2 or C3 or C4. Are you getting me? Are you getting me? I need not wait for the carry to be, because everything is reference to Ci. Everything is reference to Ci. So if I now draw my PG diagram, propagate, generate, that's why I'm saying I'm representing the diagram in terms of P and G functions. So I'm saying here, my Ci is available to me. Ci is available to me, and I have all the bit operands available here, and I'm computing G0. G1 is available here. G0, G1 mixed together to get a G01, second step. I have G01 available here. Mix it with G2 to get G02. I have G02 available here. Mix it with G3 to get G03. The moment G01 is available to me, I have the Ci available, which immediately gives me the carry at this position and the sum at this position. Similarly, the moment G02 is available to me, I mix it immediately with Ci, which is known to me, and this value would be sum and carry at this position can be immediately computed. Okay, but you can see every time you compute a new block generate function, it is always one step delay included in that, which is similar to something which I understand in terms of carry. Exactly similar. Okay. Now, whenever you draw this diagram, it is very customary to draw this diagram for a adder architecture, because the depth of this diagram denotes your timing. It denotes your time. Larger the depth, more is the time. We want to always, this is known as a PG tree. Propagate and generate tree diagram. And we want always to reduce the depth of this tree, because reducing the depth means reducing the overall delay. Here I need 16 steps to compute all 16 operations, 16 bits. This is a representative of a RCA operation. For a 16, I can draw the similar for a 32-bit. Now, this is you are combining, look here, you are combining 2 bits together. You are combining at a time 2 groups, 2 positions are combined together. Okay? I am combining G0 and G0 and 1 to get G01. Whatever is G01 available, I combine it with 2 to get G02. At a time, only 2 positions are combined. So this is Radix 2 architecture. I call it as a Radix 2 architecture. Okay, now as I said, I am always interested in reducing the depth. Now anybody can say, why not go for Radix 3? Why not go for Radix 4? Yes, you can go. And you should go. But the moment you go for Radix 3, you should understand, or immediately you should look at what possible be the penalty you are paying. Radix 3 means now it's very easy for me to generate a G02. Why should I wait for G01? I can combine G0, G1, G2 together to get G02 in the second step itself. That will be Radix 3. When you go for Radix 3, the depth of the tree reduces. That's what I desire. So why going for Radix 2? Why not going for Radix 3? Why not going for Radix 4? So Radix helps in reducing the depth of the tree. But then when you increase the Radix, what's the penalty you are paying? Can you anticipate? Now your circuits are becoming complex, because your G02 would have been only G0 ANDed with G1. Simple. A 2-input AND gate would have sufficed. Okay, now when you go for a 3 blocks to be combined together, you require a 3-input AND gate. Or you require a 4-input AND gate to get a G04 together in the single step itself. So as you know, the NAND gate chain is increasing. 4 inputs, 3 inputs. Okay, naturally the delay is increasing. So circuit delay would be increasing as you go on increasing the Radix. Because a 2-input AND gate will be simpler than a 2-input for 3-input AND gate or a 4-input AND gate. So how far you can make complexity increase, that decision you have to take. So Radix implementation, which Radix you will choose, normally is decided by the complexity of the circuits at each level. Should I go for Radix 2? Should I increase to Radix 3? You need to decide by looking at the circuit complexity. If circuit complexity is too much, that it is better to compute it in 2 steps rather than going for its computation only in 1 step. So so if it is overpowering, the circuit delay is overpowering the total 1 step plus 1 step delay, why should I go for Radix 2? Because it is increasing. Though the depth is increasing, but the circuit delay itself is also overpowering the computation. So that decision you have to take.
So does this mean that we can actually come up with some optimum Radix value?
Yes, you can do that. So is Radix 3 optimum or Radix 4 optimum? You can express everything in terms of n bit and then divide and you can go for the minimization of that equation. You can do and find out an analytical result that which one is more optimum. So write the delay expression and then minimize the delay with respect to the Radix. So that Radix now you have to write an equation in terms of radices.
But then that
Radix can be say n yes. Can be 2, n can be 3, n can be 4. You have to make Radix a variable. Accordingly, you have to define your delay equation. And then minimize it with respect to Radix. And then find out the condition.
For each adder, we would have a different optimum Radix value.
Yes.
Yeah. Okay.
Yes. But choosing an optimum Radix is also one of the way for reducing the depth of the tree. And when I said depth of the tree is reduced, means my delay is reduced. So just by looking at the tree diagram, you can immediately find out or have an idea, or you can compare the two adder architectures, parallel adder architectures. Okay, and this is what I would be slowly doing as I start modifying my RC. Aim is to now how to compute now all 16 bits in less depth. Here the depth of the tree is 50 or 60. I am not looking at the pre-computational block where I am computing all G0, P0. I am also not looking at the post-computation where I am using a finally CI to get the Cout and sum. Those steps, they are common to all adder architectures. So those two steps are removed. In between PG tree, that is looked at. Okay. So now if I make a very simple modification, all of you must be knowing a very simple modification made to this. How will you have? What is that simple modification? You know the structure carry skip adder? It is the RCA which is modified, or it is also called as carry bypass. What is the you can say the innovation in that? What is the thinking in that? What are you bypassing here? What are you skipping here? They are saying look at the 4 blocks or 4 G0, 0 to 0 bit, 1 bit, 2 bit, 3 bit. Look at 4 bits together. And then see if there is a carry generate. Then why should you wait for 4 positions to be computed? Because in any way, carry would be generated out of it, because all generate functions are 1. All generate functions are 1. So look at the generate function of each one of the 4 generate functions are 1, add them together and get me the carry out. Because anyway it would be generated. Do not wait for carry out to come from every bit position. It's called as a skip. You skip the entire 4 block. Just look at the generate functions. If all are 1, add them together and then simply have that to come at the output. Simple. 4 blocks. 4 blocks taken together. Then somebody says, look at the propagate. Okay, if there is a generate at the first position and all P functions at the subsequent 3-bit positions are, all P functions are 1, then also you need not do anything, because whatever is your C out, C in will come to C in. Or simply if your C in is 1 and all functions are P, all P functions are 1, don't do anything. Do not go for any further computation. Simply propagate C into C out of that 4-bit block. What are you saving here? You are just looking at G and P functions. You are only computing G and P functions, and then you are not computing anything further. You are not computing C1, C0, C2, C3. You are not computing. It will take delay. Rather, all 5 or 4 P functions, adding them together and then producing a C. How many steps you are taking in computing the C out of this 4-bit block? First generate GP functions, and then 4 NAND gate operation, and then AND gate operation, and then you are having a final output. No? So 2-step function. Otherwise you would have taken how many steps? First G and P functions, then computing C0, then computing C1, then computing C2, and then computing C3. How many steps you would have taken? 5 steps reduced to 2 steps. Thinking in the mind that your 4-input AND gate you are using will have a more delay. Or a 4-input OR gate maybe. No, OR gate will not have a more delay, but AND gate might be having more delay. Because OR is, we know OR is all parallel combinations in the pull down block. So OR is simpler than AND, or NOR is simpler than NAND. We know that. Clear? So this is the philosophy behind a carry skip or a carry bypass adder. So you take 4 blocks, 4 full adders, and look at it as a block, and then find a bypass path. Find a bypass path. So find out, this can immediately move in here. Condition is looking at individual P and G functions at 4-bit positions. It is a modification, a very simple modification done in RC. How will we express your T adder for this? So suppose it is 16-bit adder. I am having a group of 4 each. So how many groups will be there? 4. I am taking the worst case combination. So there is a carry generation at the 0th bit, whereas everywhere it is a propagate. Can you give me the expression for T addition? For this adder, under this condition. Can you draw the PG diagram for this architecture? First of all, what will be T addition? What will be T addition? Expression for T addition. T setup means calculation of G and P functions at every bit location. So G0, P0, G1, P1, G2, P. That is a T setup. And then there are n number of bits. And out of it 4 blocks each. So M is 4. M is 4. So N is the total number of bits. M is the number of bits in each block. So can I say it comes out to be T setup plus MT carry, assuming that you have a C in 1 and then everywhere it is a propagate. Everywhere it is a propagate. Then it would be M times T carry. No, through bypass path, first path, second path, third path. Is it clear? No. First stage generation. So 4 it will take because all are not propagate. First stage is generate. And then rest are all propagate. So that means carry in will not propagate to carry out because first stage propagate function is 0. First bit position, 0th bit position, propagate function is 0. So if I add them together, P0, P1, P2, P3, you will not get any carry out. It would be 0. Because here we are assuming first bit is generation and rest is all propagation. Okay, so M is 4 for the first block. M is 4, so it will not go through bypass path. Bypass path will not generate a carry for me, rather it will be generated first place and then it will propagate to first position, second bit position, third bit position. So 4 delays will be there. So M times T carry. 4 delay steps will be there. 1 generation, 3 propagation. Clear? So M times T carry, assuming all carry operations taking the same delay. M times T carry. After that, how many bypass will be there? How many bypass will be there? This one and this one and this one. Okay? 3 bypass will be there. What is N? N is 16, M is 4. So N by M is 4. 4 minus 1, 3. 3 times T bypass. 3 times T bypass. Can I stop here? Can I not include other 2 terms because my final C16 has come to me? Can I say C15 has come to me? Carry at the 15th bit position has come to me. Carry at 3rd bit position, carry at 7th bit position, carry at 11th bit position and carry at 15th. They all have come to me, all carries. They would be computing within that time. Can I stop here? No, because yes, and some output also has to be open. So you have to write the full equation. That will be the maximum delay time. That will be the maximum delay time. So I will have n by m minus 1 T bypass. What is this for? This is when you get this value. When you get this value, see, you are getting this path and then through this bypass, this carry over here is obtained. But this sum at the 16-bit, 15-bit position is not. I have to get the sum also. Now to get the sum at the 15th bit position, this C15 will not help you. It requires C14. It requires C14. So I have to generate, I have to wait till C14 comes. And C14 will come through this path. Once you get C11, then wait to get C12, wait to get C13, wait to get C14. And then wait to get the sum 15. get the sum 15. So 1 sum delay and rest m minus 1 t carry. Clear? Okay, so this is the expression for a carry bypass error. Okay, and here if you can make your blocks bigger in size, you can, m can be made larger. Okay, will it help you in reducing t adder? If I make m of say 6 blocks wide or 5 blocks wide, it depends on me how much, what is the number of bits I am taking in one block. How will it help you in reducing the t adder? No, I'm saying, will it help you? Will it help you by making m large? It will not help you. Because if m is large, anyway the m term will be expanding. The term which is carrying m, that will anyway would be expanding. N by m may be reducing. But m term would be, so this will not help you actually. It will not help you. But then it has been, as you said, we can find an optimum value for radix 4. I'm saying this is again, you are having a block of 4. You are combining 4 blocks together. You are computing G04 as such, because G04 is becoming, or P04 is becoming your output carry. You are taking 4 bit positions together. You are computing P04 or G04. Okay, so in this situation, what if I choose a block of 3? What radix you are changing? You are changing the radix. Radix 3, radix 4 compute, have a 3 blocks, have 4 blocks, have 6 blocks at a time. Sorry, 6 bits block, or a 4 bit block, or a 2 bit block. Okay, so now here is a question that if this, so people they thought about it. How to make the blocks? What is the optimum way of making the blocks? Should they be uniform? Should it be varying? So the one of the argument was that you take, this is 4 bit 0 to 3. This is 4 bit 0 to 3. So 4 bit 0 to 3. So 1 unit delay for computing all G and P functions. Here, 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 here it is common. Then 1 unit delay for computing the P04. By that time, what is this doing? So what is this doing? It will be GP functions, individual calculation, then 1 extra step for computing P04, and then it is passing through this mux. Another delay will come, and then C out is generated. That will be your C3, which is going as input to the next 4 bit block. So can you see, by this time, this would have, instead of 4 bit block, I could have made it as a 5 bit block. Because my first block is taking the normal 4 bit delay or normal 1 step delay plus extra additional delay to generate a C3. So that additional delay I can now, during this I can make my next block to carry, have 1 extra bit. So I can have a scaled up version. That first block can be 4 bit or 2 bit. Second block can be 3 bit. Next block can be 4 bit. Next block can be 6 bit. Can it go on in the similar manner? Will it help you? No. Because last block will be tremendously large. This will not help you. Rather, it would be better to have a tapered kind of architecture. So you have increasing, coming to a certain value of the number of bits per block and then coming down. This is known as a variable skip. Variable skip pattern. And you can find out now the best way to size the blocks. 2 bits, or should it be 3 bits first, then 4 bit, then 6 bit? Now you decide. Or you find out some analytical reasoning for finding out that. Now this kind of architecture is called as variable carry skip, where you are not uniformly sizing all the blocks. Rather, every block has a variable number of bits in that. How to have that, you can decide on that. Or you can find an analytical expression to find out the best way for making the variability or the size of the block. So this is called as a variable carry skip. Now next is, so this is the PG diagram of my carry bypass adder or a carry skip adder. Look at the depth of the tree. It is reduced. It is reduced. How many levels you want? So initially you are getting this G0. So sum will come here. This sum will come here. This sum will come here. Then you need not wait for this. From here you will immediately get this carry. From here you will immediately get this carry. From here you will immediately get this carry. So what is your critical delay path? Maybe initially these many steps, and then from here do not, you don't have to go through this. Come from here to here, come from here to here, and because this will not help you, I have to find out the sum at the 15th bit position, go through this. How many steps you have? 1, maybe from here 1, 2, 3, 4. Okay, 5, 6, 7, 8, 9, 10. Earlier it was 16 steps reduced to only 10 steps. The depth of the tree has been reduced. From 16 to we have come down to 10. So naturally I would be having a lesser D. So a very simple change, and yet it lead to some performance improvement. So there was another architecture. Everybody knows further on that. What is that? Carry select. So can you do the analysis for carry select? Everybody? Okay. So do the analysis for carry select. Okay. So we will do it. I think the period is over. Okay. So Goa campus students, thank you. Any query you have? Do you have any query? Any question?
No, ma'am.
Okay. I hope you all have started your an assignment 1 Viva. It has been started because I would be requiring those marks. I have Mr. Gavax is there.
Yes,
Mr.
ma'am.
Joshi? Is Mr. Joshi there?
Yeah, ma'am. I'm here.
So Joshi ji, kindly do all the Viva, and then I will be needing the marks because we need to do the mid-semester grading of these students.
Yeah, ma'am. I'm in the process.
Oh. And all students you have received, you have informed all of them about your, everybody has got your schedule. Kindly inform me prior to, like every day you should tell me that who are the groups who would be coming to me. Okay?
Ma'am, there will be presentation for the assignments, right?
Yes, there would be a PPT presentation, and if your lab is available to you, because in our case at Campilani campus, lab is not available because there is another course, Viva is going on. So I am taking presentations. You may take demonstrations. You may decide on that. If your lab is available, you can go in for demonstration of their work also.
Okay, yeah, sure.